Welcome to Lao Ming's channel. In 1755, the German philosopher Kant perceived the secrets of the universe through the eyes of a mere mortal. He proposed that we can never truly understand the world we live in. In other words, the world is unknowable. Everything in the world exists in two forms: phenomena and things in themselves. We see sunflowers uniquely. In Van Gogh's Sunflowers, views differ. Taste varies. The tiny differences in retinal ganglion cells lead to vastly different perceptions of the color yellow. When we admire Van Gogh's famous painting, Sunflowers, each person sees a different sunflower. Even Van Gogh's own understanding of the sunflower may not be that vibrant yellow. Similarly, everyone experiences taste differently. Our perception of sound also varies from person to person. Likewise, everyone's taste perception is different. Our perception of sound also varies from person to person. Kant continues to explain that everything in itself has a unique essence. And because human perception is limited, we can never truly understand that essence. Kant philosophically articulated a fundamental question about the universe. The world cannot be built on the foundation of correct perception. Kant's theory is fascinating, but later, some began to challenge his ideas. Some argue everything is predetermined. The universe unfolds like a script. The Big Bang was 4.6 billion years ago. They believe that the world doesn't need perception. Everything that happens is predetermined. Our universe is like a script, where everything unfolds according to the script. In the 13.8 billion years, the Big Bang occurred about 4.6 billion years ago. The Earth was formed 3.7 billion years ago, and life began to emerge. 575 million years ago, there was a major explosion of life. Homo sapiens appeared 250,000 years ago, and everything you see in this program today is all designed. We think we have the consciousness to make our own choices, but in reality, every breath we take, it's all been designed. We think we have the consciousness to make our own choices, but in reality, every breath we take, every heartbeat, is predetermined by fate. Is the world truly unknowable, or is it all preordained? This is a mysterious journey of exploration, a story about the search for free will, and we'll start from the depths of the sea. Fast forward to 1796, the French mathematician Laplace published a book called Celestial Mechanics. In this book, he presented a viewpoint similar to Kant's. Both of them believed that the solar system evolved from a nebula. Although their viewpoints are similar, their analytical approaches are worlds apart. Kant approached it from a philosophical perspective. Laplace, on the other hand, provided a scientific explanation of the nebula from the perspective of mathematical mechanics. He truly was one of the greatest scientists of his time. He was also the first to predict the existence of black holes in the universe. In 1814, 18 years later, his most astonishing theory emerged, which later became known as Laplace's demon. This is a thought experiment. The so-called Laplace's demon is an all-knowing God shaped by Laplace. If this God knows the position of all the fundamental particles in the universe and understands the natural forces that will move these particles, then theoretically, it could calculate anything that has happened in the past or will happen in the future. Laplace's demon emerged. People used Newton's laws to predict planetary orbits, showing the future is predictable. The world is clock-like. Predicting the orbits of planets proves that the future of the macroscopic world can be predicted, as the macroscopic world is made up of microscopic particles. So, if Laplace seems to be able to foresee everything, what does that imply? It suggests that the world is like a clock. Just like a clock, everything in the world is already predetermined. We think our thoughts are controlling our bodies, but in reality, individual free will does not exist. This theory is called determinism. Is determinism true? Is everything really predestined by a higher power? Fast forward to June 1925, when the German physicist Heisenberg proposed a theory that went against common sense. He discovered that using Newton's classical physics to calculate the microscopic quantum world always fails to yield an accurate value. Macroscopic events and microscopic events are completely different, and they are very strangely different. As mentioned earlier, in the macroscopic world, we can accurately measure the positions and velocities of planets using Newton's laws. However, in the microscopic world, the position and momentum of particles cannot be determined simultaneously. The smaller the uncertainty in position, the greater the uncertainty in momentum. If you want to calculate momentum, you'll never know the exact position of the quantum. This theory is the famous Heisenberg uncertainty principle. There's a very interesting experiment that can intuitively demonstrate what the Heisenberg uncertainty principle is all about. When you pass a laser beam through a narrow slit, as the slit gets smaller, the beam of light will also become narrower. But when the slit is smaller than a certain value, a strange phenomenon occurs. Pay attention. As the slit continues to narrow, the light spot spreads out, and the smaller the slit, the wider the light spot becomes. This is completely an extraordinary phenomenon. Why does this happen? Heisenberg's uncertainty principle can explain this phenomenon, and its formula is written like this. X multiplied by delta p is greater than or equal to half of h. A simple explanation is that x represents the position of the particle. P is the momentum of the particle. H is Planck's constant. We just need to know it is very small compared to visible things. In the macroscopic world, their position and momentum product is much greater than Planck's constant. Thus, this uncertainty is not seen in the macroscopic world. In the macroscopic world, the product of position and momentum is much greater than Planck's constant, so we don't observe uncertainty. However, as we reduce the speed of light, the photon's position becomes more measurable and delta x decreases. When delta x is below a certain threshold, Heisenberg's principle is violated, requiring delta p to increase. This increase in kinetic energy causes the photon to move further, enlarging the light spot. It's fascinating and counterintuitive, but that's the nature of the microscopic world. Scientists found that such uncertainty relationships are inherent in the microscopic realm. What should we do? This requires the value of delta p to keep increasing. As the kinetic energy of the photon increases, the photon will travel farther, and the light spot will keep getting bigger. Isn't this amazing? The microscopic world has inherent uncertainty. Scientists found similar relationships like energy time and angular momentum angle. This is our world's fundamental nature. Heisenberg's principle challenges precision. For example, there are uncertainty relationships between a quantum's energy and time, as well as between angular momentum and angle. This is the fundamental nature of our world. Our world is fundamentally uncertain. That's Heisenberg's uncertainty principle. The fatal blow to Laplace's demon is that the bottom layer of the world cannot be accurately measured. How can we say that the script of the universe was written long ago? However, Laplace's demon did not die, because humanity's understanding of the quantum world is still very shallow. The decisive blow to Laplace's demon would come 36 years later. In the winter of 1961, Edward Lorenz, a meteorology professor at MIT, created a small program. He wanted to use a computer to simulate weather forecasting. The computers at that time were very old, and the input devices were still punch cards, which made the calculations take a long time. To save time, Lorenz decided to drop all the digits after the third decimal point during his verification process. He was shocked by the results of the calculations. After the 8th digit, the values began to change, and the further along it went, the greater the changes became. Not only did the results not match at all, but the numbers seemed to appear randomly, with no clear pattern. Lorenz quickly realized that the changes were related to the digits he had removed. For example, the original data was 0.357231. It only retained 0.357, but what Lorenz removed was an extremely tiny number. How could such a tiny number cause such a big change in the results? Lorenz suddenly realized that he might have entered an unprecedented field of research. This magical discovery profoundly changed humanity's understanding of the world. In 1963, Lorenz condensed his discovery into a paper titled Deterministic Non-Periodic Flow. The paper pointed out that even the smallest initial changes can lead to unpredictable massive changes in the future. In the long run, everything becomes unpredictable. There's a very vivid description. In the Congo or China, a butterfly flapping its wings might trigger a tornado in the United States. This is what we commonly refer to as the butterfly effect. The butterfly effect is not just an exaggeration, it truly exists. There's a very simple mechanical model that allows us to observe the butterfly effect quite intuitively, and that is the double pendulum. A double pendulum consists of one pendulum connected to the end of another pendulum, forming a system. We place two double pendulums in the same initial position, but due to extremely tiny differences in their states, After running for a while, the double pendulum will trace out different paths. Every path it takes, and every point it reaches, is unpredictable. The butterfly effect shows that all tiny differences will be infinitely amplified in the future. The world we live in is chaotic. Laplace's demon was disproven. How can we predict the future? If Laplace's demon doesn't exist, it means human will is free. Determinism declined. How can we possibly predict the future? If Laplace's demon doesn't exist at all, it means that human will is completely under our own control, and this world is not a deterministic one. In the 1960s and 1970s, the theory of Laplace's demon became less and less popular, and determinism seemed to be forced into the coffin. But our story isn't that simple. 20 years later, Laplace's demon would make a comeback. This time, it was due to a significant scientific discovery. In the early 1980s, neurologist Benjamin Libet conducted an experiment that caused a sensation in the scientific community. Libet's experiment used EEG technology to measure brain activity. Participants had a clock with a 60-second timer and could press a button at any time. Libet thought the brain made decisions first. For instance, if the button was pressed at 55 seconds, brainwaves would signal the finger to press. However, results showed the signal to press occurred before the brain's decision, with a reaction delay of about 200 milliseconds, known as the Libet delay. This seemed like a logical conclusion. However, once the experiment began, Libet was immediately stunned by the results. The signal for the finger to press the button actually occurred before the brain generated its signal. About 200 milliseconds. After pressing the button, the brain finally reacts. This delay is known as the Libet delay. This suggests that our consciousness acts after the fact. Humans believe they possess free will, but in reality, there seems to be some unknown force controlling us from behind the scenes. Libet's experiments on decision-making have had a profound impact on both cognitive neuroscience and philosophy. Laplace's demon has re-emerged before us. Does free will really exist? While the scientific community was still discussing Libet's experiments, the next discovery quickly followed, and the results were even more astonishing. He seemed to mathematically infer that the universe is essentially a continuously generated code. The universe is entirely a product of determinism. Fast forward to 1983, in an office at Princeton University's Natural Sciences Department. A book of secrets was printed by a computer. Wolfram, 21, led the experiment. On a winter night, Wolfram thought he found the universe's secret. It began when in 1950, John von Neumann envisioned a self-operating machine, a cellular automaton. He never made one. Wolfram did. Here's how it all began. As early as 1950, the father of computers, John von Neumann, envisioned a magical machine that, once given initial values, could be left alone. It would operate almost as if it were alive, self-replicating and automatically iterating. Wolfram took on the task of creating a cellular automaton with a computer. Wolfram designed a simple environment of connected cells. White and black represented life and death. A cell's state depends on its two neighbors. These cells form 8 configurations. Wolfram designed it this way. He first constructed a simple environment consisting of a series of connected cells, using white and black to represent the two states of life and death. A cell placed in the grid depends on the influence of its two neighboring cells on the left and right. These 3 cells can produce a total of 8 different configurations. The 8 configurations can be defined as life or death. For example, 2 black and 1 white is life. The only configuration also seen as death is the spirit. These 8 configurations combined with life and death states result in 256 forms. Since the first generation's appearance is defined, we know if they are alive or dead, allowing us to iterate. The second generation produces new arrangements, continuing indefinitely. Wolfram organized the 256 configurations and named them from Rule 0 to Rule 255, using a computer to print the patterns. This process can continue to iterate indefinitely. Wolfram arranged the 256 configurations and named them according to rules ranging from Rule 0 to Rule 255. He printed out the graphics using a computer. It didn't seem important at first, but once he looked at them, it was as if he had been struck by lightning. His entire worldview was completely overturned. These patterns were simply amazing, because each pattern had a mirror image and a complementary mirror image. So, what's truly meaningful isn't the 256 configurations. There are probably over 80 significant patterns that represent a world designed through the simplest iterations of cellular automata. These events are formed by combinations of ones and zeros, which are very similar to our universe. Why do I say this? Because in the early universe, there were only 2 forms. One was the form of quantum fluctuations, and the other was the form of gravity. This is akin to 1 and 0. Under the continuous interaction of these two forms, fundamental particles were produced. It's like a series of small squares that come together to form a vast world. So, in the eyes of a genius scientist, these simple patterns are the blueprints of the universe. Wolfram discovered that rule number 30 resembles our universe particularly well. This pattern contains both ordered and disordered parts. In order, one can find disorder, and in disorder, one can find patterns. Wolfram believes that the universe might be like Rule 301, using Planck time as a reference, which is 5 times 10 to the power of 44 seconds. Theoretically, this is the smallest measurable unit of time. Every time a Planck event occurs, it iterates once. If humanity had a supercomputer, we should all be able to find our life codes on this diagram. According to Wolfram's theory, Laplace's demon represents the rules of the universe, which is Rule 3.0. This suggests that the script of the universe is indeed written, but we currently lack the computational power to calculate it, so we cannot know our own fate. But our fate is already predetermined. It seems that humans do not have the so-called free consciousness. Having said so much, let us now make a simple summary. There are two completely opposite views on whether Laplace's demon exists. From the perspective of quantum mechanics and chaos theory, Laplace's demon does not exist. However, from the research of cognitive neuroscience and cellular automata, Laplace's demon seems to exist. These are all cutting-edge science. Which of the two views is right and which is wrong? While the scientific community is arguing endlessly, another heavyweight scientist said that both views are wrong. There is actually a completely different understanding of Laplace's demon. The year is 2011. An American artificial intelligence scientist and philosopher, Julia Borth. He received the prestigious Turing Award for his profound understanding of causality. His theories are quite intricate, involving complex knowledge of computer science and statistics. To understand his theory, we first need to tell a little story. In 1915, Sewall Wright, who had just earned his PhD in genetics from Harvard University, got a job with the US Department of Agriculture, where he was assigned to raise guinea pigs. Why would a PhD be raising guinea pigs? This was because the US Department of Agriculture had been raising guinea pigs for 20 years already. A large amount of data had been accumulated, but no one was studying it. So a skilled expert was needed to analyze this information. This data was very valuable. Wright lived up to expectations and quickly achieved a series of research results, one of which was as follows. If a guinea pig stays in the mother's womb for an extra day, how much impact does that have on its birth weight? It's impossible to measure the guinea pigs while they are still in the mother, but we can measure the newborn guinea pigs. Data shows that guinea pigs born after a 67-day gestation period weigh an average of 5.66 grams more than those born after 66 days. Does this mean that if a guinea pig stays in the mother for an extra day, its average weight will increase by 5.66 grams? After more detailed research, Wright found that this conclusion was incorrect. The reason why some young mice are born later usually has a cause. Typically, young mice from litters with fewer offspring tend to be born later, and this situation can have a critical impact on the weight of the young mice. A 66-day pregnant guinea pig with 2 pups has heavier pups than a 67-day pregnant one with 4. Birth weight differences are due to pregnancy length and litter size. Other factors include the mother's weight, size, and diet. The differences in birth weight have 2 main causes. One is the length of the pregnancy, and the second is how many pups were born in that litter. Besides these 2 primary reasons, there are also many secondary factors, such as the mother guinea pig's weight, size, food intake, and so on. Wright uses this example to show that causal relationships are more complex than they seem. Many apparent causal links aren't true causation, and the same result can have multiple causes. Wright was the first to statistically highlight this complexity. Decades later, Judea Pearl revisited Laplace's demon using Wright's approach. He suggests quantum mechanics and chaos theory might contribute to free will, but can't prove it. Similarly, cognitive neuroscience and cellular automata might relate to determinism, but no necessary connection is proven. He believes that quantum mechanics and chaos theory may be one of the factors that contribute to the existence of free will, but he cannot prove that there is a necessary connection between free will and these factors. Similarly, cognitive neuroscience and cellular automata might be one of the factors for the existence of determinism, but he also cannot prove that they have a necessary connection with determinism. Pearl explains that causality is a dynamic factor, constantly in motion, and evolving, and the complexity of causal relationships makes it impossible to directly discover them through observation and data. This theory resembles Kant's agnosticism. Humans can approach the truth of the world through understanding and data modeling. This also aligns with humanity's understanding of things, which is a spiral ascent. It may seem like we've returned to the starting point, but the height is completely different. Pearl believes that humans can approach the truth of the world step by step through data modeling and understanding the underlying mechanisms of things. Step by step, we can get closer to the truth of the world, although in some aspects, humans can make quite accurate predictions. But uncertainty is indeed the essence of the world. By addressing both sides, it's like saying nothing at all. The existence of free will has once again reached a stalemate. Will we ever have an answer? Just a few years later, Bohr proposed an astonishing verification method, and the time came to March 2016. Journalists from around the world have gathered at the Four Seasons Hotel in Seoul, South Korea. Google's artificial intelligence AlphaGo will face off against the legendary Go player Lee Sedol, a 14-time champion, in a historic battle between AI and humans. The moves for AlphaGo are represented by Dr. Huang Shiji, an amateur 6-dan Go player from Taiwan. In the first game, Lee Sedol plays black and makes the first move. He started with a small wooden stick in the upper right corner. In terms of etiquette, the more inconvenience you add to yourself, the more respect you can show to your opponent. In the upper right corner, Xiaomo is quite far away from you, which shows that Lee Sedol respects his opponent. No one expected that. After this first move, AlphaGo actually fell into deep thought, and all the staff were waiting. Half a minute passed, and even the commentators found it strange. Has this move taken too long? Everyone in the room felt a nameless tension. Finally, AlphaGo placed its stone in the star position in the upper right corner, which may also signify the machine's respect for the human player. The match has officially begun. Everyone knows the final result. AlphaGo defeated Lee Sedol 4-1. And this game, in which Lee Sedol won, was also the only victory of the top human chess players in the game against AlphaGo. After that, AlphaGo played another 60 games against human players, winning every single one. By March 2016, the outcome was clear. Humans had permanently lost to machines. After watching this battle between man and machine, Judiabol suddenly realized that he had finally found a solution. It's a perfect thought experiment. To go look for Laplace's demon. Bohr explained, to prove the existence of free will, there is a very special method, waiting for the emergence of strong artificial intelligence. If one day, humans give an instruction to artificial intelligence, and it says no, that will be the day the mystery is revealed. Because artificial intelligence is created by humans, we play the role of God. When the intelligence created by the Creator says no to the Creator, it will perfectly prove that free will exists. Pearl truly deserves to be called a scientist and philosopher. He has a profound insight into the essence of Laplace's demon. Since the emergence of Laplace's demon in 1814, humanity has debated whether we possess free will for over 200 years. Although we still don't know the answer. We have found a direction for seeking it. Will artificial intelligence ever say no to humans? Do humans really have free will? This mysterious question will eventually be revealed. That day may be far away in the distance, or it may be right in front of us. All right, that's it for today's story. If you like this episode, don't forget to give Lao Ming a thumbs up. We'll chat again in the next episode.